Thank you. So as said, I'm going to show the vector value problems. Okay, so as a civil engineer, I would argue that in real life, most of the partial differential equations are really a system of equations. So their solutions are usually vector valued, like displacements or velocity. As an example, here we will use widely established in mechanics elasticity problem. So the goal of this presentation is to show how to solve vector field problems in MoFEM in 2D and 3D cases, implement and solve nonlinear problem, and also simple methods how you can verify the convergence and tangent stiffness matrix. So let's consider an isotropic linear elastic body under prescribed body forces, boundary conditions, and the displacements. So our problem is to find displacements that satisfy the balance of linear momentum and those boundary conditions. We will use here the simple small strain kinematics. And again, the weak form is established for the finite element method using Starter-Galenking approach, resulting in this set of discretized equations. To approximate the displacements and variance of displacements, we are using hierarchical shape functions that Lukas talked about earlier. So we plug them into our weak form, so we can assemble the global system Ku equals F, where the element finite element matrices are divided. The matrix is divided like four, like here, and for the element vector, you can see below when we take the contribution of the tractions on the boundary and the gravity forces on the entire domain. And these integrals are calculated using Gauss quadrature, and in that form we can directly use them for our computation. So here we start dissecting the code. Again, we will begin with the setup as in other cases, which is pretty much similar as in scalar problem. Note that here at the very top of our program, we're going to have this constant expression, which will be the integer that will define the dimension of our space. So when we are adding fields here, when you have a domain field U in the space H1 and I base, for 2D problem, we will have the space dimension of 2. So our shape functions will have, we will have two coefficients. And for 3D case, when we want to compile the program for 3, we're going to have 3 coefficients. So we also have to specify the boundary field that will give us access to the pipeline that operates on the boundary, so we can play with some boundary conditions on the boundary itself, not only on the domain. And again, we have this parameter that we can, from the command line, change the order of approximation. So in the next function of our main program, we need to define the data that will be passed between the operators. So in case of elasticity, we need to compute the elasticity tensor using this formula below. So we will use here the F-tensor library that can very neatly exploit the Einstein notation and do this computation for us without any loops and in a very efficient way. And what is nice about this form is equation is that depending on the coefficient A here, we can have a case for plane stress or 3D or plane strain as we defined here, the if statement. Next, we will implement, we will implement the boundary conditions in our main function. So for that, we use the MoFEM function. So to enforce the Dirichlet boundary condition, this function, what it will do, it will remove the degrees of freedom for our problem. So if we are considering the cantilever beam like this in our meshing software, we can choose the particular set, let's say this face of triangles, and we're going to name it fix all. So what the program will do is will remove all the degrees of freedom from that face, and that will be not considered a tariff problem. So this will be a homogeneous boundary condition, simply specifying the displacements to be 0. So it will be a classical cantilever beam. To set up the Neumann boundary condition, we are going to use the operator from the MoFEM library. As you see, we have alias OP body force that is going to use OP base times vector, because this is exactly how we have to integrate our body force. And in order to pass what is the value of this vector, we will just hard code it for the case of simplicity of this example, that it will always be value of -1 in the y direction for 2D and 3D case. And this boundary is by definition applied on the and this load is applied by definition on the entire domain. But of course, if we want to, we can implement it such that it can be different materials with different weights, etc. Next, we are going to in the next function of our main program, we will be pushing the operators to the left-hand side pipeline. And again, we can use the operator from the library of MoFEM. In this case, in order to assemble this matrix, we will use OP grad sim tensor grad. So exactly what we need: calculate the gradient of the shape function, that's fourth order tensor, which is our elasticity tensor, times another gradient on the columns. And in case of 2D case, we will also need to compute the inverse of the Jacobian, as Hoang described. And in the next element of our main function, we will have setting up the solver. This will be exactly the same as in previous cases for scalar problems. So thanks to the pipeline manager that we are using, the moment we are creating the solver, the KSP will already know which functions to trigger in order to compute our global matrix M and the global vector F. So the moment this line here is triggered, the system will be assembled and then solved using PETC. And the last thing that we need in our program is to define the post-processing. So we are going to use one of our pipelines and clean it and push another set of operators once we obtain our displacements. So it will be useful to compute strains and stresses. And I will explain what this set of operators is doing. So the first one, OP calculate vector field, simply calculating the matrix of the deformation gradient at each post-processing point, and then this matrix is passed to the OP symmetrized tensor. This is also, all of them are already also in the MoFEM library, so no one has to re-implement them again, although they are very simple. So this OP symmetrized tensor computes the small strain tensor, which is then used by another operator to compute the Cauchy stress. And finally, the last operator will take this data that we compute and save it on the nodes in the form of so-called tags of the MOAB database that we can later, so that we can save this file and visualize, and visualize using, for example, ParaView, like was shown before. So here we will compile first the 3D case. In order to execute our program, we will have to specify what is our mesh. So we take our 3D mesh and specify that the order is, for example, 2. But if for tetrahedral meshes, it could be any number from 1 to 8. So as to remind you, we are considering cantilever beam with uniform body force, and the MB convert tool is used, as was shown in scalar example to post-process the result. So this is the output already post-processed and warped by the displacement vector, so we can observe the displacements of this beam. And if we change this parameter, of course, without any problems, we can calculate the 2D case for triangular meshes. As you can see, these two results are quite similar, even though this one is in a plane stress. One thing that is worth to note here is that this beam is unrealistically swelling at the end, as you can see, and elongating. And this is the consequence of the small strain formulation that we use. So small strain formulation, it is well known, in fact, cannot deal with large rotations. In order to better visualize this, I applied this only rotation on this simple toy example to show you how it generates some spurious deformation in case of large rotations. In order to mitigate this issue, we can introduce finite strain formulation. So in that case, we will use a simple Hencky stress measure that can properly take these rotations into account without generating any spurious strains. This approach makes it possible to extend classical small strain constitutive relation into the finite setting that we need. It is applicable when we deal with large rotations and moderate strains and effects like plasticity. But in that case, we just consider elastic part. So as you can see, the logarithmic strain is defined as a logarithm of the product of our deformation gradient. The work conjugate stress is defined like this. It has no physical meaning, but Professor Mie proposed so-called post-processor. So if we compute the second order, if we compute the derivative of this logarithm product, then we can basically project it back into first Piola-Kirchhoff stress that we can then directly plug into our balance equation. But now, because when we use it, this logarithmic strain measure will make our problem nonlinear. So the best way to solve it will be in increments using Newton-Raphson. So our previous balance equation can be restated as a F internal minus the external force. And this internal nonlinear part can be expanded in the Taylor series, and while neglecting the higher order terms, we can now obtain the increment of this nonlinear function. This derivative is called tangent stiffness matrix. So we can assemble this in the new system for new linear system for calculating the increments. And if we solve it in a series of linear problems, our residual will consecutively decrease until we get satisfyingly low error. So in order to implement this, the general structure of the code will stay the same. We just have to push some new operators that will compute the Hencky strain measure. So this is quite a long list, but only to make our program more modular and plug in some eventual additional effects. But everything can be computed in one operator. So I gathered everything here. So we heavily exploit the ftensor library to do nicely all these tensor operations. So first we calculate the stress measures, the formation gradient, and the right Cauchy green. Then we need to compute the logarithm of this, but typically it's quite a difficult task, but we already have functions, generic functions that can compute any function of a tensor that we need. So this is done automatically, this logarithm. Then later we need this projection tensor, compute the derivative of this product. And again, we can use another function in MoFEM that can do that for us. And finally, for tangent operator, we need a second second derivative of this product. Second derivative of this product, as you see, contracted with this stress T. So we have a contraction of second order tensor with sixth order tensor, and that is also handled for us in the function that is already existing in MoFEM. So with those quantities calculated and pushed in the proper operators, we can then focus on the last two operators. First one that we add to the left hand side that will compute and assemble the tangent stiffness matrix. So it is very similar to our linear case, but now instead of D, we are using this tangent operator C. And then for the right hand side, now we need to add the operator that will compute our internal force that includes the first Piola-Kirchhoff stress. For setting up the solver, this time we are going to use time solver, which has a nonlinear solver included, embedded in, and it can also handle for us the time stepping. So for example, if we want to use some kind of adaptivity, we can do it very easily by using time solver from PETC. Next thing that we have to define here is the so-called monitor. So that monitor is a function that will include some routines that we want to be executed after every load successful converged load increment. So for example, error estimator, post-processing, or calculation of a reaction in case of elastic problem. And then the final calculation, the final execution of the program will happen here in the TS solved. So thanks to the pipeline manager, the solver will already know which functions, which operator to use in order for every increment to assemble the left-hand side and the right-hand side for our problem. So this is the solution for the 3D case. As you can see, again, we specify for the second order. And additionally, we have this TSDT, which is the size of our increments, load increments, and this is the result. So on the left hand side, we have our old result for the small strains, and on the right we have large strains. And so we effectively solve the problem of this unrealistic swelling and elongation that happens in this simple small strain formulation. If we look at the output of our program for each load step, we can see this nonlinear solver residuals, how they are converging. And as you can see here, they are forming the holy grail of nonlinear problems, which is the quadratic convergence. However, this is not always the case. As a developer, developers spend a lot of time debugging this particular element of our nonlinear problems, because even small mistake in this tangent stiffness matrix might cause the convergence to be no longer quadratic or basically diverged at all. But thanks to this integration with PETC, we can use these nice tools like that are using finite difference method to compute our stiffness matrix, basically only looking at our right-hand side equation. So if you use this additional parameter here, we can compute what is the error of our relative and absolute error of our implemented matrix with the one computed with the finite difference method. Of course, this is very slow and not usable for practical applications, but for debugging and finding mistakes is great. We can also display all the entries of our matrix and see this difference in real. Sometimes this is good for spotting some simple mistake like missing coefficient 0.5 or similar silly mistakes. What can be also useful is visualizing the tangents stiffness matrix and the errors, especially when we have coupled problems with many fields. Then we can identify that only one of them is, for example, creating the issue, so we know which exact operator is assembling, for example, this part of the matrix, and this is the one that has to be fixed in order to achieve the quadratic convergence. Okay. Thank you. I mean, and in summary, I showed you how to solve the vector value problems in MoFEM using operators from the library, and some tools for debugging tangent matrix. I hope that you feel more aware of MoFEM modular structure. As Ignatius showed, we can easily add, we can easily compute problems with many fields. And for example, I extend this problem, this nonlinear elasticity that I showed by adding some adding contact and plasticity fields. And as you can see, we can compute this simple beam that is elastically deformed until the contact with a rigid cylinder. And this kind of example is also available in the tutorials under the section advanced. And okay, that will be everything. Thank you for your attention.
Thank you, Karol, for